Hello everybody, welcome to our first Astro Coffee Hangout for 2018. My name is Tony Darnell, I run deepastronomy.space, and we've got a great hangout planned for you today. We're going to be talking about something that I never really thought much about until Carol came up with this idea for this particular hangout series, and this is a result of talks and some of the things that she learned while at the latest AAS meeting in January. We're going to talk all about that, but we're going to be learning about what do you do when you're trying to navigate the solar system, but you don't have access to the GPS satellites that we're also used to seeing. And NASA's been working on this. They've got some really interesting tools that we are going to be discussing for navigating the solar system using pulsars. And we also are going to be talking about some of the instruments on board the ISS that are currently using some of this software. So we will be getting to that here in just a moment. But I want to tell everybody that 2018 is a big year for deep astronomy. We're trying a bunch of new things. And I would like to just take a brief moment and say that if you like these Hangouts and you would like to see them continue, we hope you'll continue. There's a number of ways that you can help support what we're doing here and our efforts. The one way is to become a Patreon patron, and that would be a big way in which you could financially help support the Hangout series that we're doing here. And anything helps, anything from $1 to $1 billion. And, you know, $1 billion obviously helps more.
Would be good.
Yeah. But that's not the only way. There's plenty of ways you can support what we're doing here. You like the videos that you're watching. Give us a thumbs up. Share out the videos to people that in your circle to sort of help spread the word that this is going on. And leave comments. Interact with us during the Hangouts. All of these things really help show your support for the Hangout series. So please, please feel free to do that, and we would definitely appreciate that sort of support. Now, another little, not a big change, but a change that we're doing this year, at least that I'm trying to do, is because we are streaming on 4 different platforms: YouTube, Facebook, Twitch, and Periscope. It's hard for me to get all the chat clients in one to monitor all of those. I have Carl's help. He's helping me out a lot with monitoring these. But if possible, please go to deepastronomy.space/live. There is a app right there. It's our Discord server that I am looking at right here. It's my main way I'm looking, and looking at your chats already, and already Adam Synergy's there, Uncle Bill's there, Black Knight's there, and so I'm watching that. I'm also going to be watching the other things, and so will Carl. But you really make it nice if you could help support our Discord server, and what that does is it keeps the chat live even after the stream ends. In YouTube, if you're on the YouTube live chat, when the stream ends, it's gone. It's just, I don't get to capture any of that. And I'm always logged in to the Discord server. So please use that as well. Okay, so enough of that. Let me bring up my my co-hosts and actually everybody now. Hi, Carol. Carol Christian. Hey. You may remember she's my co-host, and without her, these don't happen. So hi, Carol. It's good to see you again.
Hey. Yeah, that's great. Welcome to 2018.
Well, 2018. We're finally back on.
I'm looking forward to it. Yeah.
Yeah. So, you want to give us a little background on the Hangouts, and maybe say who's bringing them to us, things like that?
Sure. I won't share any hang-ups, but Hangouts.
Did I say hang-ups? Share with us your hang-ups, Carol.
Yeah. No, I think you can figure that out. The Hangouts are really an informal chat with the scientists and engineers who are doing the current research in astrophysics and space exploration. So we have the series of 4. And Afternoon Astronomy Coffee, as many of you know, is like what we do in our research institutions, sit around and talk about research topics that interest us, but in this case, we actually have the people doing it. So we're really fortunate to have the nicer people here to talk to us about this great project. And the Hangouts are supported by the American Astronomical Society and the American Astronautical Society, and we thank them for their support.
Absolutely. Okay, great. So thank you, Carol. So here we are with our first topic of the day. And our guests are all from the Goddard Space Flight Center. And And let's see, I think the best way, so that I'm not clicking constantly, I'm just going to start. So in the upper left is Carl Clark. He's my assistant. He's the one that's live tweeting these chats. Hi, Carl. It's good to see you again. He's also monitoring all the other chats that I can't monitor, and we will get to your questions and comments. So please give our guests some good questions, and we will read them out in a little bit later. Right next to Carl is hang on, let me get my window up. Is Dr. Jason Mitchell. He is like I said, all these guys are from Goddard. He is an assistant chief technologist at the and he's a project manager for Sextant, which is one of the projects we're going to be talking about today. And Sextant stands for Station Explorer for X-ray Timing and Navigation Technology. Welcome, Jason.
Thank you. Thanks for having me.
Yeah, you're welcome. And directly on next to him on the right is Dr. Luke Winternitz. He's a project scientist. He's the project scientist for the Sextant for the Sextant, and he's a navigation engineer at the Navigation Group. Hi, Luke.
Hi.
And also below, right next to Carol, is Dr. Zavin Azermanian. He's the science lead for the NICER instrument on the ISS, which stands for Neutron Star Interior Composition Explorer. And we did a hangout on NICER I think it was over a year ago with Harley on Future in Space. So check out that NICER hangout that we did as well to learn a little bit more about that. But welcome, Zavin.
Thank you. Good to be here.
And finally, right next to him is Dr. Keith Gendreau. He's the principal investigator for NICER as well. Hi, Keith.
Hello.
Okay, so where should we start? Should we start with a background on NICER or with Sextant? What's the most logical place to start? Now, as I understand it, Sextant is a software package that is being used on NICER. Or should we maybe talk a little bit about the problem we're trying to solve? This idea of navigating the
talk about NICER.
Okay, start with NICER.
Talk about it.
Okay.
That's my vote.
Okay. That has a lot of weight with me, Carol. Okay, so give us some background on NICER. Keith, maybe?
So NICER is the Neutron Star Interior Composition Explorer. It's an explorer mission of opportunity that was competitively selected a few years ago, and on the International Space Station now after launch just this past summer in June on a SpaceX rocket. It's an X-ray telescope, and it's got a science component as well as a technology component. And so it's this interesting marriage of science and technology. The science component is to understand ultra-dense matter by doing X-ray timing of pulsars. We do this with an instrument that has a collection of 56. We have 52 functioning X-ray telescopes. They look like this, about the size of a coffee can. They concentrate X-ray photons down onto a detector that detects individual X-ray photons from a pulsar. We measure the energy of each photon, and we measure the arrival time of each photon very accurately. And our science has to do with building extremely deep light curves of the pulsations of pulsars, looking specifically at the shapes of these pulsars to work out the equation of state of the neutron star. We also have this technology component. So when we put together the NICER mission concept, we reached out to the technology component of NASA headquarters, the Space Technology Mission Directorate, and they supported a fraction of our mission to do a technology demo that uses a subset of the pulsars that we're doing our science with to do what's been considered pretty much ever since pulsars were discovered about 50 years ago. Use them as a way of plotting out where we are in the galaxy, and in a very practical sense as a navigation tool. So we got about a quarter of our funding from STMD, and that became the Sextant part of the NICER mission. And like you said, Sextant it's flight software that's kind of sniffing the data coming out of our instrument within the flight computer, and it works out a navigation solution. But there's also a ground aspect. People analyze the data, and they try to update and improve the algorithm. So NICER embodies both the science and technology.
Okay, can you hold up that thing you had up before? What was that? That was this is the, now hold it up end on so we can see the little concentric, is there concentric cones in there or no?
This is one nicer concentrator. It's got 24 different X-ray concentrators or parabolas that concentrate light down to a focus that would be way behind it about a meter or so. And so we use this to capture photons from faint pulsars onto a small detector, and that gives us a large signal with relatively little noise. And these are grazing incidence optics, and as I kind of point this at my camera, you can kind of see that you can see through it. It's
yeah, that's what I was hoping to show. That's really amazing. So those are concentric tubes in there that vary, as you say, grazing incidents. It's hard to focus. It's hard to reflect an X-ray, and so you guys do that with these and I think Chandra does it the same way as well. You just basically try and move the X-ray a little bit, right?
Yeah, they nudge them. I mean, X-rays typically reflect at very, very shallow angles as opposed to a normal incidence. The X-ray hit a mirror at normal incidence, it would get stuck in there before it came out. At grazing angle, it can reflect.
Now, did you say there were 24 of those?
So, so we have 24 in each one of these concentrators, and then we have 56 on NICER.
Yeah, 56 concentrators. I like that name, by the way, concentrator.
Yeah, it's a concentrator. It's actually not an imager. More like a magnifying glass in some sense. We just concentrate light down to a spot just to increase the signal.
Wow. Okay. And Zavin, since you work on NICER, do you have something you'd like to add to that, or is a little more context, maybe?
Sure. As Keith mentioned, pulsars were discovered just 50 years ago, a little more than 50. They were discovered in 1967, first published in 1968. So some people are making noise about that first publication this year. We thought it was fitting that
took a while, huh?
that a mission, the first mission dedicated to studying neutron stars, pulsars, would happen on the 50th anniversary, half a century. It's hard to believe. But even when they were first discovered, people were puzzled by them. So these are stars that, and we still are today, these are stars that are basically the lighthouses of the universe. They are extremely small, about the size of a city. And, for those of us here in the Washington, D.C. area, you could fit a neutron star inside the D.C. Beltway, the ring road that goes around the city. They're the densest stuff in the universe that we know of. You could squeeze 2 suns into one of these neutron stars. And they're the most magnetic objects that we know about, magnetic fields trillions of times stronger than the Earth. They're the fastest spinning stars that we know of. They're the fastest highest velocity stars, the fastest moving stars that we know of. They're basically the most outrageous objects that most people have never heard of. But because their magnetic fields are so strong, they shine most brightly at their magnetic poles, the north and south magnetic poles. And because they're spinning, that light, which is very beamed, highly beamed, gets swept around the sky. And if we happen to be in the path of one of those sweeping beams, we see a flash every time the beam goes by. And that's a pulse of light. And so they became known as pulsars.
I'm sorry to interrupt.
Yeah.
I just want to is the magnetic field of a neutron star closely aligned with its spin axis, or is it kind of like Earth, where our spin axis and our magnetic poles are a little bit different?
There's no relation. Some are aligned and some are completely misaligned.
So you can have this sort of sweeping rotational axis going round and round in a certain way, but the magnetic field is more like a beam of light coming out of the equator. I mean, with the poles, I mean.
Yeah, the poles can be aligned with the equator, or they can be aligned with the spin axis, or anywhere in between. Just like the planets in the solar system. If I'm not mistaken, the planet Uranus has a magnetic field that's at 90 degrees to the spin axis, and Earth's is only 11 or 12 or 15, I forget, degrees. misaligned. But those misalignments for neutron stars can be anywhere. And so the beams can sweep around either very little or cover essentially the whole sky.
And how does NICER look at the interior of these?
Right. So NICER's scientific objective is to understand what neutron stars are made of, to understand the densest matter, the densest state of matter that nature allows. Any more dense, and you'd get black holes instead of neutron stars.
There's a name for that. It's some kind of degeneracy, isn't it? Or am I thinking?
Yes. So Fermi pressure, Fermi degeneracy is what holds a neutron star up and prevents it from collapsing, and that's a quantum mechanical effect that is probably not worth getting into in detail now. But basically, the neutrons that make up most of the bulk of the star repel each other at some level, and that pressure holds off the crushing weight of the outer layers of the star. But we're talking about basically a giant atomic nucleus, something that's as dense as the nucleus of an iron or a uranium atom, only denser, several times denser, and the size of a city.
Okay.
So to answer your question, how NICER does it, basically these stars are strongly gravitating, and we look at the effect of gravity on the path of light that's emitted by the neutron star. We look at gravitational light bending to try and understand the density of the star. And once we know the density, measure the radius and the mass to get the density. Once we know the density, then we can figure out what the interior is made of.
Which gravitational light bending? Not from the neutron star.
Yes, indeed, from the star itself. So the surface emission of the star is actually bent around. It wraps around the star because of the lensing from the strong gravity of the star.
It lenses itself.
Yep. A quick picture in your mind might be, imagine two hotspots at the north and south magnetic poles of the star, and the star is spinning. So if the star were a beach ball, you'd see the hotspot on the near side, but you wouldn't see any emission from the hotspot on the far side. But it's not a beach ball, it's strongly gravitating. And so some of the emission from the hotspot on the backside actually wraps around the star and reaches a distant observer. And how much of that emission gets lensed out to the observer tells us what the density of the star must be.
I can't even begin to imagine that in my mind, what that must be like. So it's kind of wrapping around. You can see the light from the other side. That's really cool.
Right.
Yeah, that hurts my brain. Okay, so I guess we know what NICER's doing, and NICER is doing very accurate timings, and it's helping us understand the interiors of neutron stars. How do neutron stars help us figure out where we are? You guys were saying you wanted to that they help us find our location more accurately in the galaxy. How do they do that? Who wants to go? Luke, Jason, we haven't heard from you yet.
Sure. You want me to take it, Jason?
Yeah.
Sure.
Okay.
Well, so basically it comes down to the stability of that pulsation. So some of these pulsars are, a subset of them are extremely stable, like almost atomic clock-like stable, or actually atomic clock-like stable. And that stability that's also present in the GPS system. So the radio emissions from the GPS satellites are all synchronized and very stable. And that's really what allows us to navigate with GPS. So you can precisely time the arrival of the signals from GPS and navigate with that. And so the same principle kind of applies for pulsar navigation, also called XNAV. So that stability and that predictability of those pulsations sort of enables the navigation.
So hang on. So with GPS satellites that we're all very familiar with, they work because we accurately know where those where those satellites are in relation to each other, and we also know a lot about, and their signals are precisely do they have synchronized with each other?
Right.
So a GPS receiver on Earth is going to receive as many of these signals as it can get that it's in range for, and use the differences in those signal arrival times maybe as a location. Am I getting that right?
Yeah, that's right.
Okay.
So you can compute the range to those satellites by timing the signal, and in GPS's case, you know where the satellites are, so that allows you to navigate that way. With pulsars, it's a little different, but stability comes into play because you can very accurately predict what the phase of arrival is at any kind of reference location. So the way that it works for Sexton is we have a model of the phase of arrival of each of the pulsars at the center of the Earth, or we could do that at the center of the solar system. And then by measuring the phase on the spacecraft, or on the ISS in the case of Sexton, we can figure out that difference. So if the phase arrives a little bit early, from our point of view, then we know we're on a certain side of this, along the line of sight of the Earth's center, for example. And then we can do that to multiple pulsars and measure, kind of get information about navigation that way.
Okay. So Tashin and Dark Time, I see your questions on Discord. I'm going to ask it in a minute. But I just want to make sure I'm getting my head around what I'm seeing. So I get the idea of the GPS signals, the locations of the satellites, and I understand a little bit how GPS receivers might work. But to me, it seems like, okay, and you're saying, okay, well, fine, we've got naturally occurring GPS satellites out here in the form of these pulsars.
Right.
But that seems to me like, now we know where the GPS satellites are to great precision because they're just in geosynchronous orbit or wherever they are. And but a pulsar, you've got to have some pretty good astrometry on these pulsars in order to get any kind of accuracy from them, right? I mean, you got to know exactly where they are to a pretty high precision, right? How do we do that?
You don't actually. What you need to know is you can figure out if you have a model. You can develop models by observing these pulsars with radio telescopes on the ground for how the phase evolves at a reference location. So that could be the center of the Earth, for example. And you can have that stored on board your spacecraft. And because they're so stable, that model can work for months and years. And so if you know when the phase is supposed to arrive at the center of the Earth and you measure the phase on your spacecraft and it's arriving early, then you know that you're on a certain side of you're on the line of sight to that pulsar. So you need to know the direction to the pulsar, but you don't need to know accurately the position of the pulsar.
But how do you know when it's going to accurately get to the center of the Earth then, if you don't know its position? Because
we develop models from observing these pulsars on the ground with radio observatories that are around the Earth. So there's a ground segment component to this
okay, so there's a model that based on the signal,
right.
Based on the signal from the pulsar will tell you accurately enough where, when it's going to arrive at the center of the Earth, and then the difference between that and where it actually gets received.
Where you observe it, yeah.
Where you observe is where you can get your position from.
That gives you information along that line of sight to that particular pulsar.
Okay.
Does the model evolve then? Over time, it changes a little bit, so you would have to update the model every once in a while. Is that
yes, but
on board?
Because that's where the stability comes in. Is that the model? I mean, the models are complex, and Zavin could speak more to this, but there's lots of physics behind those models. But the pulsations are stable in the sense that they can be predicted for very long periods of time. And the models don't need to be updated very often, like months or even years.
Okay, and Uncle Bill is commenting, it's all relative, Tony. You only need to know how the phases change relative to the Earth and other spacecraft observers. Okay. Okay, I think I'm getting this. Now, how accurate is this, guys? This software? How accurate? I mean, we know what GPS is accurate to within, what, 3 meters? Something like that? 10 feet, I believe. Yeah. So how accurate is this? And can we use it instead of GPS?
Not as good as GPS. So the pulsars are timed to about a microsecond, and that translates to kilometers. And our mission goal is to get to 10 kilometers of navigation. So
10 kilometers.
that's not so good on the Earth's surface or near the Earth compared to GPS. But when you're out in deep space, that could be fully adequate. And we have a stated goal of getting to 10 kilometers and a stretch goal of getting to 1 kilometer. So those are the sextant goals. And now the benefit to XNAV, of course, we fly missions into deep space.
And XNAV, you mean X-ray navigation? Is that what that's for? Or?
Yeah, that's
okay.
Right. So
okay.
XNAV is one of the.
Now that's cool.
Yeah. But the main benefit of XNAV, so we have technology now to navigate into deep space. NASA uses mainly the Deep Space Network, which are large radio telescopes that communicate to the spacecraft and also provide range and Doppler measurements that can be used to navigate. But as you get further and further from the Earth, these measurement types, the navigation accuracy kind of degrades because the baseline of the Earth becomes, the angle is smaller and smaller as you get further out.
And not only that, but the speed of light time gets a little bit impractical after a certain distance, doesn't it? I mean, just the fact that it takes so long to get signals back and forth from Earth.
Sure. Yeah. For autonomy, that's an issue.
Yeah.
But in principle, XNAV doesn't have that downside. That it should work kind of roughly as good near the Earth as it does out in deep space.
Okay. All right. So, Jason, can you give us some sense of how old is the Sextant project? How long have you been working on this software?
So there was some early efforts that started back in 2009, or maybe even earlier than that. I joined in 2000, like at the end of 2009, beginning 2010. So, and I suspect that maybe Luke can remind me. There was some initial work a few years before that in terms of what we call here IRAD, which is internal research and development. And so those are ideas that are proposed by the folks doing the work that are interesting. And then if it looks like that's a seed that can germinate, then it can be selected for funding for additional work. And that's kind of how all this stuff started.
And where is Sextant? Presuming that it all gets worked out to everyone's satisfaction. I mean, this is a technology demonstrator. I'm getting that sense. Where do you see this being used in the future?
Well, there's the kind of potentially short or near-term goals that we would look to infuse into some additional missions. There's also the long-term goals, which what would XNAV enable you to do? There's some mission concept, solar gravitational lens mission, where you would want to send a spacecraft to the gravitational lens point of the sun, which kind of begins at 550 AU. And would extend for up to another 100 AU, depending on where you want to move the spacecraft to use the sun as a gravitational lens. And if you're that far away, you would certainly like to have much more autonomy in your spacecraft, and you wouldn't want to have to rely on constant communication back to the Earth to be able to do your navigation. You can imagine that for solar gravitational lens location, you'd have to spend a lot of time because you wouldn't be moving very much in the sky. At 550 AU. So you'd want that autonomy on board to be able to do that. And then another option that we are exploring right now is also infusion as autonomous backup for crewed missions. One of the things that is always the instance that you don't ever want to have happen with the crewed mission is loss of communication.
Right.
And if that's the case, and you have crew on board, you would like to make sure that they have all the tools available to them to maintain their position knowledge so that they could reestablish communication. Because unfortunately, if they don't have those kinds of tools, then you're kind of limited to what you can do on the ground to try and connect back up versus having some onboard autonomous capability to help the crew reconnect.
I think I'd want that as my primary. If it was me, I'd want that as my primary system. And then if that went bad, I can call Earth and say, "Yo, we just lost our pulsars." Just because that seems more reliable than relying on something that's progressively getting further and further away from me. Okay. Well, so wait a minute. I got to get back to this point. So the sun has a gravitational lensing point 550 AU away. how was that? I guess it's a little bit beyond the. I'm just going to talk about that a little bit because I didn't know this. What scientific value does that get you? Do you get, by going to that point, can you see things that have been gravitationally lensed by the sun more powerfully? I mean, what does that get you? What's that good
so
for?
Again, remember, I'm an engineer.
I know. I did.
Technologist.
It just caught my attention.
Probably Keith and Zavin can elaborate more, but you're exactly right. The point is that you use the sun's gravity to lens light, and you end up with kind of a toroidal ring around the sun that gives you higher resolution, potentially to the point for relatively near planetary stars that have planetary systems. You could potentially gain enough resolution to inspect the atmosphere of the planet in some detail, and in fact, even get images, maybe at the hundreds of kilometers resolution, so you could actually see some pixels of the planet itself.
Okay, you heard it here first, folks. I'm predicting that instead of L2, where everybody's sending all these space telescopes now because it's so great gravitationally around the Earth, that's where we're going to be sending the next generation of space telescopes.
That's where we should send Hubble in 2020.
Yes, 550 AU away, and make it more powerful, and then it will put JWST on its knees.
Some year.
You heard it here first, folks. I'm telling you.
Some year.
We're going to call it the sun grav lens point. That's what we'll call it. Okay. All right, you heard it here first. I'm just telling you. Okay, let's get to a couple questions because I've been waiting. Tashin, he's also Philip W. on the other chat. He's got question for the panel. Does the navigation system have a minimum range? Would it get better if it was closer you got to Earth? Anyone? Does it have a range? I mean, you got to be able to get the X-rays, or you got to be able to get the signal from the pulsar. So as long as you're receiving it, right, it works.
I think this is I guess I'm maybe not clear on the question. Is that as long as you can see the pulsars and you can get signal, it'll work. The challenge is the dynamics involved in your trajectory. So the nice thing about the demonstration with NICER is that since we're on ISS, we're in a relatively high dynamic orbit. And Keith and Zavin may chastise me for this analogy, but I think of NICER as kind of an X-ray bucket. We want to collect a bunch of X-rays to make a measurement, so we want to fill up the bucket. But if we're moving very fast, it's kind of challenging to fill up the bucket because you go around and you fill up a little bit, and then you got to come around again and fill up a bit. So that makes producing the measurement a challenge for us. Whereas in the say a trajectory to an outer planet that's fairly quiescent, you can stare for long periods of time, so it's relatively easy to fill up your bucket. There's not really, and that would be something that you would tune your models to for the flight regime that you would be operating in. So, there's not necessarily kind of a minimum range where you would want to be, say, around a gravitational body, or you would prefer to be in free space. As long as you can receive the X-rays, you should be able to function perfectly well. And the accuracy would be limited to effectively what your collecting area is, or how much signal you can get over the time period you want to make the measurement.
Yeah, but this business about comparing it with when it would get to the Earth's center, do you need some other reference point when you're traveling out in deep space?
Yeah, you could. So you can define that reference point to be anywhere. And, for example, it could be at the solar system barycenter would be a logical place to put it. I think that's where they do most of the pulsar timing analysis. Or you could define it along a reference trajectory or that goes out into deep space if you kind of knew where you were going. So you do need that model, and that model is based off ground-based observation. So there may be some degradation when you get very far from the Earth based on a model that is developed on Earth-based observations.
Right.
Yeah.
Okay.
Or even if it's projected down to along your trajectory or at the solar system barycenter. But in principle, it may be possible also to just develop the timing model kind of on board with your own observations, and that's something that we've discussed.
Okay, all right.
So I have a question. I have a question.
Relieve that issue.
A clarification question. So, as you go out in the solar system, we want to do this exploration, and you're positing that this technique might be helpful. it seems to me, and maybe this is a naive notion, but we kind of know where Voyager is. So that would seem to be a benchmark of what we can do using traditional techniques, right? And so we want to be better than that. Voyager is out there navigating, we know where it is, and it knows where it is, right? So, or is that very inaccurate?
I'm not sure how accurate they navigate Voyager to, but I think we think of it as possibly an alternative. One of the benefits of XNAV is that it could be done on board autonomously versus that deep space navigation now is done on the ground with ground processing of radiometric, range and Doppler to those satellites, or maybe angles. So one of the benefits is autonomy, and then we also think of it as a complementary, and also something where maybe you could get very, very good range information from the ground-based observations, but the plane of sky view you could do better with XNAV, perhaps. We like to think of it as complementary or possibly alternative.
So Jason, you guys did a simulation for the Cassini mission to kind of talk about how NICER compares to a extensive use of deep space network as a nav solution. So you did the Cassini profile, and I forget the exact numbers, but we took one module of the 56 of NICER, and we did at the time, and I think it's now been validated by our in-flight result that we just got. We could, do better than 10 kilometers, pretty much independent of position, all the way out to Saturn, while DSN, while it had very good range information, the cross-range direction was degrading well beyond 10 kilometers. In fact, we did better. For example, once you got past Jupiter or Saturn, I forget the exact where that crossing point was, but and the other part of this is, as Luke was saying, is complementary nature. The deep space network in that simulation for Cassini was that was very extensive use of the deep space network. I want to say that was 24 hours a day, 7 days a week of using these gigantic dishes all around the Earth, and that got a solution that didn't do as well as the Pulsar navigation solution.
Wow.
Is that correct, Jason?
Yeah, that's the, with DSN, you typically have this kind of few kilometer per AU degradation of the navigation solution as you move out and towards the outer planets of the solar system. And that's where we think for the deep space exploration, that's where we expect the big payoff for XNAV to be, is that becomes highly available autonomous navigation that's available on board to the navigation requirement that you've tuned to. Now, maybe your navigation requirement is you need to have a few tens of kilometers so that you can hit a B-plane spot to insert in orbit around a body. For the outer planets and outer bodies if you want to go really far and start thinking about exploring primitive bodies where you're in the Kuiper Belt or the Oort cloud even, the ephemeris uncertainty on those bodies is quite high. So if you have something that has this absolute position knowledge capability as a spacecraft coming in, then you would use your suite of relative navigation sensors that you always are going to have on board anyway to help beat down that ephemeris uncertainty and to insert and actually be able to insert in the orbit. Of course, if you've been designed to have enough fuel to do that, that's why most of those outer body explorations are just flybys, because you just don't have enough delta V to slow down, and so you just kind of fly by and take pictures as best you can, like the New Horizons mission.
Right, I was going to say New Horizons must be suffering then from the inaccuracy on its current journey, right?
The uncertainties are an issue, right? I don't know if you had watched any of the APL imaging and discussions that they had as they did their approach. It was a concern that they started looking at their cameras as they began their approach to see is everything clear? Does the path look okay? It doesn't look like we're going to have any collisions with anything big that we didn't expect until we got there, right? It's entirely possible for those outer planetary bodies to be very dark. so that you wouldn't even see them necessarily until you're right up on top of them. And so having something like this, again, this feeds the notion of complementary sensor, is that you could beat those uncertainties down and would enable those kinds of things, whereas it would require additional work to do if you wanted to beat down those uncertainties. You'd have to dedicate other resources to make that happen.
Okay, you guys were saying that when Cassini was using the Deep Space Network, it was actually using quite a bit of dish time. Is that a resource-intensive thing to be able to? I mean, does it hog up the Deep Space Network, I guess, is my question, when a spacecraft is trying to get a position or
maybe
navigation?
Maybe by way of clarification, this was for our simulation. So when we were simulating, we wanted to be the most aggressive that we possibly could in terms of dedication of DSN resources to it. I think it was basically we gave it, and Luke maybe can clarify that. I think we gave it, as Keith said, 24-hour range and Doppler. So it was using a dish whenever it was in view, 24 hours. And then there was up to 24 hours of Delta Door spread over a week's time. So that's kind of like the next level of navigation capability the DSN would provide, this kind of delta differential one-way ranging that gives you additional accuracy. And so we tried to be very aggressive with the published numbers to give it as much resources as possible so that we could obtain the best navigation resource that we could with the published numbers for DSN. And the takeaway is that during that trip, you get that degradation because plane of sky continues to get worse. Range accuracy generally stays roughly the same, but because of the baseline stays the same as you move farther and farther away, you get that degradation. Whereas because XNAV is on board and available all the time, it kind of stays flat. It stays flat to your navigation requirement.
And I think, and so as we were talking about earlier in the Hangout, and I believe Zavin, you said this, this isn't new stuff. This is the first paper was 50 years ago. Is that right? On using these pulsars. Did I remember that correctly?
The discovery of pulsars was 50 years ago. It was a few years after that, in the early 70s, when folks at JPL, at the Jet Propulsion Laboratory, realized that you could use pulsars to navigate spacecraft in deep space. But it didn't seem feasible at the time because pulsars at the time were only known as radio sources, and you needed a giant radio telescope to see the pulsations, and it wasn't sensible to carry a giant radio telescope on the back of a deep space probe. It was years later when pulsars were detected in X-rays with more compact telescopes that finally it was realized you can actually do the navigation application now in X-rays, not in radio. So I'd say that probably was that realization happened sometime in the mid to late 80s. I may be wrong about the date, but then there were lots of paper studies, hand calculations, computer simulations, up until 2 months ago, when we finally had our first in-space demonstration that this X-ray pulsar navigation actually does work.
That's amazing. And so, but that didn't stop people back in the 70s from, recognizing the promise of this technology, because I believe it's mentioned in our description here that Carol sent out that both the Pioneer and the Voyager probes that are currently out in interstellar space, or at least close to it, have this information of how to get to us via pulsars on it, right? That's right. On the spacecraft itself.
Yeah, it started with the Pioneer plaque, which has a depiction of 14 pulsars and their signals encoded in something that looks like Morse code, dots and dashes kind of thing. And any civilization that comes across either one of the Pioneer plaques or one of the Voyager records, if they can decode that diagram, can figure out where in the galaxy those spacecraft were launched from, based on the timing and the location of those 14 pulsars as they were known in about 1974. And that whole concept was developed very quickly in the span of a few weeks by Carl Sagan and Frank Drake and some of their collaborators. And it was a very last minute addition to the Pioneer spacecraft. But that's right. We're now realizing that concept of localizing, in that case, where the solar system is, but now vehicles based on pulsar signals.
So just as short wavelengths have trouble getting through our atmosphere, I can also imagine this has limitations if you're depending on X-rays. Not that we're doing it, but let's say we're going to other parts of the galaxy. Certainly things like dust clouds in the interstellar medium might get in the way of these X-rays, right? That would be the one bad part about using X-rays for this technique. Am I right? Maybe not within our own solar system, but if you're traveling to another star, passing through interstellar space, you got to worry about clouds, right? Dust and gas, mostly dust.
The X-rays, for the most part, go right through that, and actually, it's an advantage compared. Well, I mean, there's some absorption, but
okay,
there are things to worry about in the radio band where you have propagation delays when you go through plasmas, and our X-ray, frequencies that we're looking at are so high, it's above that plasma frequency, and we don't have those time delay terms. So there are actually advantages to using X-rays.
Okay, all right.
It's
so
compactness of the telescope.
Oh, well, great. Okay, so can you hold up that tube again, Keith? And you said that this is state of the art right now for this technique. You've got that concentrator, and you said how many? 50 of them are on the International Space Station?
We got 52 functioning units on space.
And are they all put together in one big grid kind of thing, or a big square kind of?
They're all in a cube.
So that's pretty big. 50 of those. Any chance it can be made smaller for some smaller probes?
Like I said, the Cassini simulation we did, we took one of the 50.
Oh, okay.
And that's what that comparison was against.
I see. I didn't hear the part about.
We put 56 on NICER because NICER is also a science mission, and we wanted to pack as much X-ray telescope into the volume we're allowed to play with on space station to do our science. So we did an optimal filling approach to pack as much telescope in there.
Did NICER by any chance have any observations? This is a little bit of a tangent. Did they have any of those observations of that neutron star merger last year?
We tried to look. Actually, when we heard about it, we tried to look. It was just outside our visibility constraint. It was a little too close to the sun.
Ah, okay.
We have taken looks. We not quite bright enough for us to see at this point.
Okay. All right. Well, Dark Time has a couple questions. Have pulsars been used to locate the very center of the solar system, or to determine if there's a planet 9? You're laughing, Zarin.
I can take it. I can take the question. The short answer to the Planet 9 question is no. There's not yet, at least, any evidence for another planet.
I don't even know how you'd use this for that, but
from pulsar timing data. Well, it has to do with what Luke was saying about points of reference. And so, in the radio community, there have been decades-long, very high-precision timing efforts that reference all of the pulse arrival times. Not at a spacecraft or the ground or the center of the Earth, but at the center of mass of the solar system, because everything's in motion, right? The Earth is moving around the sun, and the planets, especially Jupiter, are moving the sun around. So if you take the center of mass of the solar system, that's the closest thing we have to what we call an inertial reference point.
I see. Relative
to the distant stars. And so, but the radio community, and this is just really recent work in the last year or two, the radio pulsar timers, the folks who are doing the most high precision measurements, do find that they can distinguish between different calculations for the center of mass of the solar system that come out of the group at the Jet Propulsion Laboratory and other groups, similar groups, that use that information to track spacecraft. So these things called solar system ephemerides can be used to compute where the center of mass of the solar system is. And those models improve all the time. When we look at pulsar data in comparison to an old model of the solar system versus a new model of the solar system, we can actually see the differences at the levels at the level of meters or tens of meters in where we think the center of mass of the solar system is, just from pulsar timing.
What did you say? Solar system what was it? What was that word?
Ephemerides.
Ephemerity. I learned
ephemeris.
Oh, okay. From ephemeris. Okay. Learned a new word today. Cool. All right. And Dark Time is also asking, and I'll just read it out. The military must be interested in an indestructible GPS. How good can the precision get? Well, we talked earlier that you guys were hoping to get about 10 kilometers. Is that right? Is that what you said?
With the current, our primary goal for the current experiment was to have maintain 10 kilometers of navigation uncertainty, or be better than that in terms of navigation error.
Right. So, I mean, we're a long way from them. The GPS they're currently using is way better, so they're going to be fine. All right, Carl.
Sorry, Connie. Just to finish Jason's thought, that 10-kilometer goal was achieved in November, and Jason and Luke deserve a tremendous amount of credit and their team for that achievement. And they actually got it down to 3 kilometers or so, and they have a stretch goal, which we hope to achieve sometime later this year.
So
That's great.
That is great. Congratulations. What are the parameters that increase the resolution or that increase your accuracy then? Is it the strength of the signal? What are the things that limit you in terms of being very accurate?
The signal strength, certainly.
Okay.
So that limits how accurate each individual measurement can be. But then also, at some level, it's limited by the ability of the model to predict when the pulse would arrive at the reference location. And I think that's, Zavin can speak to what the state of the art is, but I believe it's at the microsecond level, which is at least hundreds of meters.
The model of the
ability, the model of the pulse arrival times.
Okay, all right.
At the reference location.
Got it. Okay. Carl, do you have anything that I haven't asked yet? Do you see anything?
Yeah, there's a couple. So one that seems a little bit odd, so I'll lead off with that, of course. And then I have an either-or question, which will be the second one. But Alexander Reiners asks, more pulsars like in 1992 with the Lich system. So I'm entirely unfamiliar with that. Are there pulsars that orbit black holes or gas giants that don't form stars that end up orbiting these things? Does anyone know anything about the Lich system? And maybe elaborate on that a little bit, because that is definitely a curiosity.
I don't know what the Lich system might be referring to.
Right.
Pulsars have been found orbiting many types of other stars, including other neutron stars, pulsars, not yet orbiting a black hole. That's kind of a holy grail that hasn't been achieved yet in terms of the pulsar astronomy, the science side, finding a pulsar orbiting a black hole. That would be pretty cool in terms of testing our understanding of gravity and Einstein's theory of general relativity. We know of pulsars orbiting white dwarfs, main sequence stars, even planets, but not yet black holes.
Well, we need to take a phone call up to the universe and say, can you fix that up for us? The either-or question is, Larry Keese, 24, asks, parabolic or chrono... oh, good Lord, I cannot even pronounce this. Canonical concentrators. Which one is it? Parabolic or canonical concentrators? Parabolic. So there you go. A nice either-or question after my really obscure reference.
They're asking about the kind of
detector
concentrators in the detector.
Yeah. Right.
Yes.
Yeah.
Okay.
These are little parabolas, but they're very far away from the focus point, so they look like cylinders.
All right.
They're just very, very gently curved.
And then let's see. I think we might have covered this just a little bit, so I'll save it for last in case anyone wants to elaborate on anything more. But what is I think it's specifically for this current detector, what is the maximum distance that we're able to detect or use pulsar navigation with? So like they're asking about, so how far away are the pulsars that we're looking at to use pulsar navigation?
Well, that's a good question. Do you have any favorites? Any like reference pulsars you use the most? Or how far away are they?
Yeah, and that's Luthra. What is the maximum distance the pulsar navigation can detect pulsars?
So, and I think we can detect all sorts of pulsars, but the navigation demonstration that's going on is making use of some relatively nearby pulsars, and if we just directly took the method we had and apply it, it would work within, tens of parsecs from around here. But as Luke mentioned, we could bootstrap, we could start looking at other pulsars as we go out deeper in space, and we could, we can imagine the system evolving to make use of the pulsar terrain out there.
Okay, and there's a clarification on that Lich system, by the way. It's a millisecond pulsar 1,000 light years away in Virgo, around which the first confirmed exoplanets were detected. That was from Paranor 001. So that's what he was talking about.
Thanks, Paranor.
Yeah, appreciate that. Okay, and then we're running out of time. I want to get one more question in from Dark Time. How big radio dishes does one need to measure the pulsars? Obviously, in radio. How big were they that were used?
I've personally seen pulsars easily detected with a 40-meter diameter dish. For comparison, the Deep Space Network dishes, the biggest ones are 76 meters in diameter. I know that people have struggled with single dishes that are smaller than, say, 10 or 15 meters. So you'd need, if you're just working with one dish, something at least that big, probably much bigger, to see especially the millisecond pulsars that are useful for navigation.
Right. Okay. All right. Well, just real quick before we sign off, what is next for you guys? What's next for Pulsar and for NICER? Are you guys just going to keep making observations of neutron stars with NICER, or where do you guys? What's the next step?
NICER's baseline mission goes for another year.
Okay.
Continue looking at a number of neutron stars and other things in the sky. Just this morning, we got a request from a Japanese group to look at a star that was flaring, and we did a target of opportunity observation of that. Probably this spring, we'll try to do another pulsar navigation power hour or day or a couple of days to see if we can pull in some of the better millisecond pulsars that we didn't have in November to get a better solution. The instrument is, we think, a good general purpose X-ray observatory, and we're hoping that beyond our baseline mission end date in January next year, we could proceed with a guest observer program and go on as long as we're producing good science results through our senior review process.
Okay, and for Sextant, you just going to keep on going, keep writing software?
Well, so for us, it'll become infusion activities. What other missions? We're in some discussions with some folks to see about infusing our technology into their mission, and to try and get over that operational hump transition. Right now, we're TRL 7 with NICER. We'd like to get to the technology readiness level that would enable operations, which is kind of the 8-9 range. So hammer out the requirements that we have to do to support the ground segment, as Luke alluded to, which is similar on the GPS side. So we have a ground segment so that we can maintain those pulsar timing models. And maybe that would potentially eventually include a space segment where there could be X-ray timing continued in space to be able to support X-ray navigation as well as general timing maintenance. And then we have a few other technology items to explore with NICER. I'll leave it to Keith to decide if he wants to mention any of those that we'll be continuing to pursue with NICER. They're related.
Okay.
Yeah. So I think one of the exciting things that we're going to try in about a year or so is when we wanted to make sure that this pulsar navigation thing would work, we developed an X-ray source that we could modulate arbitrarily, and we did in-lab pulsar navigation demonstrations to work out the algorithms. If you come by my lab, you'll see that we use the same X-ray source to transmit data. So you can see iTunes transmitted by X-ray modulation. So we are actually going to put an X-ray source on the other side of space station to do a demonstration in space of X-ray communication as well.
That's great.
All right. Well, thank you guys very much. I'm going to go ahead and stop us here because we're running out of time. I want to thank my guests, Dr. Luke Winternitz. He's from, and all of these guys are from Goddard. Dr. Jason Mitchell, Dr. Keith Gendreau, Dr. Zavrin Arzermanian. I'm sorry. All of these guys working on both NICER and the Sextant projects. I want to thank you guys all for being on our Hangout. I want to thank all of you guys for watching, and we'll be back. Well, I don't know if we'll be back next week. I haven't heard from Harley if we're going to have a Footsteps to Mars Hangout. I think we are, but if not, then I will see you. I'll keep up to date on our Hangout calendar, and I'll keep you posted there. Thank you all so much for watching.
Yeah, thank you so much for doing the Hangout with us. It was great.
Yes, thank you very much.
A great project.
And I'll see you.